Okay, so hello everyone. My name is Miłosz Warzecha, and yes, the topic of this presentation will be template metaprogramming, and also life in general, which may seem like an unlikely combination, but trust me, it's actually doable. So maybe before we begin, I will start by introducing a couple of things about myself and what do I actually do, and how did it happen that I had some opportunity to actually discover template metaprogramming. So I work at Nokia. I'm a C++ developer, and I work in a project called Assassin. Not to be confused with Assassin's Creed. Assassin is actually a compiler that allows you to translate a specification that's written in a notation called ASN.1. Usually in our case, it's some kind of telecommunication protocol. And Assassin allows you to translate such a specification from ASN.1 to C++ structures. And it also supports various encoding, decoding abilities to actually retrieve some kind of message from such a protocol and try to communicate with that. And it's in that particular project where I had the unique opportunity to discover template metaprogramming and to actually learn that something like that even exists, which was quite shocking to me. And I decided that I will share with you all of my learning experience or the pain and suffering that I had to endure during that process, but I will try to make it as painless as humanly possible. So, briefly, in a couple of words, what is template metaprogramming? What we will try to do in here is that we will try to shift some of the computational effort that we would normally do in our programs at runtime. We'll try to shift that to the compile time, so the compiler will do some computational effort for us. And is it worth doing so? Well, compiler could be a powerful ally to ourselves, mainly because it knows a lot of things about our program. It actually knows everything. It's, I think, impossible to know as much as the compiler does. And it's not lazy. It's better at optimizing things. It's not like if you have some kind of a task to do that may seem not that interesting, not that important to you, then compiler will happily generate code and do everything for you without any hesitation. However, template metaprogramming is a little bit of a controversial topic, as you might have maybe noticed at this conference. It's controversial because when used properly, template metaprogramming can actually provide you with lots of benefits. It can make your programs and designs more functional, more robust, and more efficient. But the thing is that if used not carefully enough and not appropriately, it could actually make you some trouble. And there are various legends going around about what are the kinds of trouble that template metaprogramming could get you into. Some people mention the C++ template syntax as being one of the problem because it's not really friendly to look at. It's not really friendly to human eye, human soul. It actually drains energy out of you, so that might be a little bit discouraging for a start. The second thing is that when something goes wrong, and it will undoubtedly go wrong many, many times, then usually you are greeted with a lot of angry compiling messages and errors that the compiler is trying to tell you all the things about that it doesn't like about your program. And usually that kind of message could span several screens of template instantiations and could take several megabytes of memory. So then you can run into problem of actually figuring out what is wrong with your program, why the compiler is yelling at you so much. And the third thing is that the infamous compilation time that could rise into a non-trivial amount, and you could run into problems of actually maintaining the stability of your whole design process, of your whole development process. So that may not sound that inspiring. However, I would like to mention a couple of things. First of all, the language changed very much. Template metaprogramming has been around since the early 90s, I think, and the language changed a lot, and we have additional features, additional capabilities that we didn't have before in the early 90s, for example, and that also affected template metaprogramming. So it's not as cumbersome as it used to be in the beginning. And the next thing, maybe even more important, is that the compiler technology went a lot forward. So the compilers are actually a lot better at handling the additional responsibility that we're trying to provide them with in template metaprogramming. So after all, it is actually quite fine to do some template metaprogramming nowadays. it's not as hurtful as it is sometimes made out to be. So, maybe what we would try to do now is to look at the first metaprogram that was ever created, and it looks something like that. And unfortunately, the lower part of the screen has been cut out, which is quite unfortunate. There's been a lot of inspiring quotes at the bottom, which I'll enumerate. So if there's something that you would like to ask about, then just remember the number of the quote, but you'll probably not be able to read the actual quote. I can read it out for you. History is just one damn thing after another is the first one. Okay, so this is the first metaprogram ever created. It was created in a secret lab by German scientists, and it's hard to figure out at a first glance what it's actually supposed to do. The task in here was to generate prime numbers and print them to the screen. And there are two things important about this program. First of all, it doesn't compile. It's even been named, I think, the most famous program that doesn't actually compile. The second thing is that it still actually works, which may sound very suspicious to you, because after all, that's not really how C++ language is supposed to work. If you don't compile a program, then you don't really have a program. However, this particular thing was supposed to compute to actually generate prime numbers and print them to the screen, and both of those things are actually accomplished. It's just the printing part is done in the error messages. So when the compiler will angrily tell you all the things that it doesn't really like about this particular program, it will actually show you all the prime numbers that it calculated. Very smart from him. And you have to appreciate, I think, that template metaprogramming actually was discovered completely by accident. Somebody was too curious, somebody went too far, and that's how template metaprogramming came into this world. A little bit similar footprint that you would see in superhero movies, where there is usually some kind of secret experiment, and then somebody is too curious, somebody goes too far, something goes wrong, and some kind of monster is created. And in this case, the monster is template metaprogramming in C++. So, what could we do to actually enter the cave of that monster? Scary and dark. The first thing is someone is really afraid of doing some compile time computations. You can use static assert. Assertions, very useful tool. You use it all the time in programming. Static assert is distinguished by the fact that you can check some constraints actually at compile time. So you can perform checking some conditions, and if those predicates are not met, then the program will not compile. For example, you could make sure that you're working on a 64-bit platform or a 32-bit platform, and what you could also make sure that you're using a particular correct version of a library, because the previous versions do not have some kind of functionality that you rely on in your design. And it is one of the safest way to actually do something at compile time. It's one of the easiest ways, and also one of the most functional. It's not like static assert will be only useful at the beginning. It will actually be useful all the time at each step along the way when you template metaprogramming. Next thing, very, very important, is type traits. Type traits are actually the fundamental things when it comes to template metaprogramming. What they are, you can think of them as tiny tools that allow you to extract some information, and particularly information about types, and then you can use that information to make some kind of intelligent decision. Of course, whether or not that decision is intelligent depends on a lot of different factors, but type traits provide a functionality of actually extracting some type informations from them. For example, you can make sure you can check if a given type is a class, or if two of the given types are the same, or if they are convertible to each other. And what is important about type traits is some of them are not that trivial to implement, but some of them are very easy. And it's a very good exercise actually to get into template metaprogramming by implementing your own type traits, which is very, very functional to get into that. So maybe let's try. First of all, remove const. And to be honest with you, the name reveals most of the functionality that we'll be doing here. So at first it might sound a little bit exotic to you. After all, const is not really an independent entity in C++. It's not like you can take const and do something interesting with it. So how could you actually grab something like that and try to remove it from a type? Well, let's see. what you have in here is a meta function. And usually when you think of a function in C++, then you have some kind of a blueprint in mind. So there is something that you give to the function in C++, something that the function takes as an input, and something that the function in C++ returns to you. And it is exactly the same in case of a meta function. What the meta function takes is a type t in that example. And what the meta function returns is this internal type declaration using type t. So if you had to analyze this particular meta function, what it actually does is that it takes a type and then returns to you the same type without doing anything. So at the beginning, you might think that that is very stupid. But that actually is because that is actually stupid. What you need is a template specialization. And it's a mechanism that we'll use all the time in template metaprogramming. We specialize this meta function so it can take a type t, but with that top-level const qualifier. So when the compiler will perform the sort of pattern magic problem, and you will try to invoke this meta function with a type, if your type contains that top-level const qualifier, then this specialization will get chosen by the compiler. And what is happening here is that the meta function takes this type and ignores the const qualifier and gives you the equivalent type t, but without this const. And that's effectively how we remove that const from the type. So let's suppose we have some kind of a type that we specifically created for this presentation, and we'll try to remove const from that. And the whole blueprint is very simple. We have the name of the meta function, we have a type as a template parameter, and we refer to the result by typing : type. And that's how we could ensure that that particular type is mutable. Let's do something else. Let's make sure that two types are actually the same. Here we have a meta function that takes two types, type t and type u. And by default, we return the answer false. So those types are not actually the same. What we then do is that we specialize this meta function. So if the first argument, if the first type that we've evoked this meta function with is a type t, and the second argument is also type t, then we return the answer true because those types are actually the same. So very easy thing. And we refer to the results in the same way as before. We have a name of the meta function and the types that we want to check, and we type : value to actually check if those types are the same or if they are different. We could also make something that is not in the standard library. We could create a meta function that will check if a type given to this meta function is a particular singular type that we're looking for. And we will first define some kind of helper structures, so we don't have to type all the time the static const something. We define some kind of helper structure so we can then inherit after them. And it looks like that. We have our primary template. By default, we return the answer false. And then we have our specialization. If that particular type that we've given to this meta function is the type that we're looking for, then we return the answer true. However, there is something that we actually forgot about in here. And it's that if we give a type to this meta function and that type contains additional qualifiers, like constants, for example, then this meta function will return false. And that's perhaps not the behavior that we've intended. And there are a couple of ways that we could fix it actually. So first of all, we could make additional specializations. For const, for volatile, for const volatile, is actually not that many specializations, so we could type all that out, and we would get all the things covered with template specializations. Second thing that we could do is that we could actually remove all the qualifiers, like we did with remove const, from the type before we hand the type to this meta function. So effectively then the meta function analyzes the type stripped of all the particular qualifiers that were there before, because they were removed. That's the second way that we could resolve this issue. The third thing, that is perhaps more fun, is that we could implement an additional meta function. And what this meta function would do is that it would take a type, and then it would also take a list of types. And in that list of types, it would contain the type that we're looking for, the type that has the const qualifier, volatile qualifier, const volatile, and we would traverse that list and find if the type given to this meta function is in that list. If it is, then we answer true. If it isn't, then we answer false. And how could such a meta function look like? Here we have our basic interface. So we take a type t, and also a list of types that we want to traverse. First of all, if the type list that we have is actually empty, then it makes no sense to actually try to find something in there. So then we return false if we encounter a type list that is actually containing no types. Second specialization is that if the type that we're looking for is at the very beginning of the list, then we return true. If you're familiar with variadic templates, basically where you have the rest of types, ... What you'll be given in here, the compiler will substitute a type, basically a comma-separated list of types. So then we can isolate the first type that is in the list and check if it is the type t, the same type that we've invoked this meta function with. And if it is, then we answer true. And what it remains for us to do, then we use compile time recursion to actually isolate again the first type in the list, but that this time this type is actually different from the type t that we invoked this meta function with. So we have a type t that we're given, and at the head of the list is type t0, so that's not what we're looking for. So then we recursively invoke this meta function, but ignoring this t0. So we have a type t and the rest of the types. So we don't have to bother with the t0, and we do that until the list is empty. So then the first specialization is triggered, or we actually find a type at the head of the list so that the second specialization is then triggered. And fixing our meta function looks like that. So we have a type t that we're giving to this meta function, and we have a list of types. So with the type that we're looking for, the type with const volatile, and it actually behaves in a way that we've intended from the beginning. This is a lot of fun. This is a magical trick, which is a new library feature in C++ 17, but it was actually perfectly doable before. And what we'll try to do in here is that we'll take a type and we'll investigate if inside that type we have a type member by a particular name. So here in that case we have a structure, we have a type called life, and we'll try to find meaning. If life has a meaning, then we return true. If there is no type member to call meaning, then we return false. So how could we actually do that? First of all, we have our primary template where we by default return the alpha false. So there is no particular type member inside that type. Then we have our specialization. That specialization takes a type t and as a first template argument, and as a second argument, we have a void t. And what we put inside the void t is this particular type member that we're looking for. So we're referring to this as t : meaning. And if it exists, then what the void t will do is that we'll take that type and turn it into void. That's basically what void t is doing. Even though it looks very non-suspicious, it's basically a different name for void. But if you notice, it actually takes a parameter pack. So when you give a list of types to void t will take all of those types, assuming they are all well-formed, and turn them into void. And that is exactly what is happening here. We give to void t the particular type member that we're looking for, so meaning in that case. And if it actually exists, then void t will take that type, turn it into void, and we will get the answer true from the template specialization that we've made. However, what if that type member doesn't actually exist in that type? What you have in here, this t : meaning, looks actually pretty lethal. We should get a compiler error if life has no meaning. So what actually is happening is FINE, one of the ugliest acronyms that actually exist, although some telecommunication acronyms would prove quite a challenge for it. At least this one is pronounceable. And what it stands for is substitution failure is not an error. So what is happening here? When you have a template in C++, we have all those different placeholders, the t's and u's and whatever name you've particularly chosen. And what the compiler will do is that at first it will try to figure out what the hell is it supposed to substitute in there. And it could now go a number of different ways. You can actually try to explicitly state what it should substitute in place of that placeholder, or the compiler can actually figure out on itself. And in C++17, you actually sometimes don't have to use the angle brackets because the compiler is smart enough and can figure out the types on itself. So first, it will try to figure out everything on its own, or if you've explicitly told the compiler, then it will choose those types. And if that's done, if that particular part of the compilation is done, then it will try to substitute. And it could go in two different ways. First of all, it could substitute the placeholder, and it will produce something well-formed, a code that is actually understandable, it makes sense, and that's usually the behavior that we've intended. So then compilation process goes on, and everything eventually finishes, hopefully without any error. The second thing, however, that could happen is that the substitution will produce code that will make absolutely no sense. Will produce code that is ill-formed. And what happens then is that the code that doesn't make sense gets discarded silently by the compiler, but without producing any compilation error. So when we refer to the T colon meaning and that type member is not in the particular type that we're investigating, then the void T will take an ill-formed type. This whole specialization on the right that we've created will be an ill-formed code, and it will get eliminated by the compiler. And so then, if we try to refer to the result of the whole meta function, we will get the result from the primary template. We will get the result false, because the specialization got eliminated by the compiler. And that's Sphina in a nutshell, which could prove very useful also in a number of different things. So for example, suppose that you have some kind of algorithm implementation. And you have implementation that is optimized for a particular type, that is optimized for particular characteristics of that type. And you also have a different implementation that is optimized for a different type. It uses the characteristics that are in the other type. So what you could do is that you could use enable if to actually choose the correct implementation of that algorithm at compile time. Enable if, in its basic form, takes a predicate. And if the predicate is satisfied, then it will give you void. Unless you want a different type from void, then you can actually provide the type that you want in the second argument. But here we actually we will do with void. So we just give a predicate to the enable if. So if the predicate is satisfied, if it is true, then enable if will return void to us. However, if it is not satisfied, then enable if will return nothing, completely nothing. So when you notice this green rectangle, where it actually is that in that place you would usually have the return type of the function. So if the predicate in the enable if is satisfied, then you will have void in there. But if it's not satisfied, you will have nothing, and that will be an ill-formed implementation. So if you give a type to this algorithm and it satisfies the first predicate in the upper part of the screen, then that implementation will be a well-formed implementation, but the second one will get eliminated by the compiler. And if you hand the type that satisfies the second predicate in the middle portion of the screen, then the first implementation will get discarded by the compiler because it will be ill-formed, but the second one will actually be the one that you will be using. And that's how you effectively can switch between implementation and implementation at compile time. However, if you provide a third type that doesn't satisfy the first predicate and the second one, that's when you actually get a compiler error, because both of those implementations got eliminated and discarded by the compiler. What is also enable if very useful for? It's useful for resolving some things that you would not expect really. So suppose you have some kind of a type, and you have a constructor, of course, and that constructor takes a string. And you want it to be very smart. You use perfect forwarding, all the modern C++ features to actually make a generic constructor for this type. So it could take a string as an L value, as an R value, whatever the way that you've actually created the string before, it will handle it in the most efficient way possible. So You also define a copy constructor and a move constructor, so you're basically doing everything in according to the most fantastic rules of the C++. Everything seems perfect until you try to use it. Because when you try to instantiate that type with a string, it will actually handle everything perfectly. It will perfectly forward everything, so the generic constructor actually works fine. That was a good idea. However, if you try to use the copy constructor, you will encounter a lot of problems. And that's because when you try to invoke the copy constructor, actually for the compiler, the better match to construct this type will be the generic constructor that we've defined earlier. And that's because the copy constructor has that additional const qualifier, which the compiler really doesn't like. So it will try to use the generic one. But the generic one is used for the strings, from constructing things from string types. So then it will produce a compilation error. So how could you resolve that? The first solution, yes, that's to further emphasize the things. The first solution, which is not really a solution but more of a hack to actually get it to compile, would be to just get rid of that const qualifier in the constructor. But that will produce a lot of problems. For example, when you try to inherit after that type, then you'll still get compilation error. So that's not really the perfect thing that we're looking for. So what we could do is to use a magic spell from template metaprogramming, and you could use enable if, which would take a predicate that would check if the type that you're given to this constructor is actually a string, or something that is easily convertible to a string. And then this constructor, this generic constructor, will be available to you. And if the type that you're invoking this constructor with is not a string or is not something convertible to it, then this whole generic implementation, this whole generic constructor will get eliminated by the compiler, because the predicate in the enable if will not be satisfied, and all this code will be formed, so it will get eliminated, and the constructor, then the compiler then will be forced to use the copy constructor, even though that it has still that const qualifier that it really didn't like at first, but now it's actually forced to. It doesn't have any other options, and you could make it a little bit more pretty, because it's not that pretty looking when you have some kind of magic spell from template metaprogramming in that particular place. So you could isolate it and then use it and even give it a name, so your code is more expressive than it was at first. One more thing that I would like to mention is that what we usually do in programming is that we rely very much on the concept of containers. So we rely on when implementing algorithm, we rely on stud vectors and lists and maps to actually implement something meaningful. So how could we end up with a similar concept for compile time computation? There are two main problems that we end up basically in here. First is a problem of design, because we're trying to construct something that will be a container for a type, because that was the main logical jump sort of in template metaprogramming, that we operate on types. And so it doesn't really make sense for us when you try to make a container for type to allocate memory for a type. It doesn't really make sense, because type carries no actual value, no actual weight, so we could allocate memory for something like that. And the second thing is that we would like to also be able to operate on integral constants, so some kind of values that are available to us at compile time. However, they are not actually types, so we have a uniformity of representation problem, and we'd like to solve that. How could we go about that? So the second thing, with integral constant, we could actually make some kind of a thin wrapper around the constant, so it will take a type and the value of that type, and then with the uniformity is actually available to us, and we can operate both on the integral constants and on types themselves. The second problem with actual representation could go a number of different ways. First try would be maybe something like that, which is not a very good idea. So we have some kind of static size of this type list, and then we define the aliases. So we actually have a type list, but it's not really flexible. is not really, you can't really insert something additional in there unless you want to make the whole thing again. So that's not really something that we could use. And that's the biggest Nicolas Cage that I've ever seen. You could also make the way that Alexandrescu popularized in a modern C++ book. We actually popularized even the notion of type lists themselves. But you could also use periodic templates, which is something that we've done before. And what it does is you have a parameter pack which on itself represents a type list very naturally. So then you can use that parameter pack to actually define a type list, and it actually also allows you to define some operations on that type list, like pushing to front or to the back, or many basic things that you actually want to be able to perform on a container usually. So how could we go about that? We could make a push front implementation. This is our basic interface, so we have a list of types, and we also provide a new element that we want to insert in front of that list. And the implementation looks like that. So we have our type list, and what we return from this meta function is this internal type declaration where we have a type list. We take the parameter pack, and we also take the new element. We insert the new element in the front, and the parameter pack goes in the rest of the type list, and that actually produces a type list with the new additional element inserted in the front, just like you wanted. And this is how we could use such a meta function. So we have a name, we have a type list that we provide to this meta function, and we refer to the result by : type. And that's how we could push to the front of a type list any given type. We could also take away something from that list, from the front, for example. So we provide a type list, and what we do is we again isolate, like in the previous example, from this parameter pack, the front type, the head of the list, and then we just ignore it. And what we return from this meta function is this internal type declaration where you have a type list, and you have the rest of the types, the tail that we've provided earlier with the head ignored. And referring the result of this meta function looks exactly like we would expect each time. What we could also do is we could append two type lists together, which is very, very easy. We have two parameter packs, and what we return from this meta function is a type list created from those parameter packs. We have a parameter pack 1 in the front, and the second parameter pack as a second argument. And we return a type list that is basically a fusion of those type lists provided in the beginning. And the invocation of this meta function looks exactly like we would expect. And there are also a couple of different simple things that we could make. We could ensure that the type list that we've created is not empty, which is very easy to do. We could also make sort of a twist on the previous implementation where we've taken out something from the type list. We could then just take the front type from the type list and return it, so we then have the knowledge of what is at the head of the type list that we've created. All of that basically can be used to provide some more meaningful operation, which would be an equivalent at compile time for a std transform algorithm that we have in the standard library. So what we can do is that we can create a meta function that would take a type list and would take a meta function, and it would apply that meta function at each of the types in the list. So how could we go on about that? We have our basic interface. It's the sort of first implementation that we could try. And it takes the type list, it takes a meta function that we want to apply, and it also checks if the list is actually empty during performing this algorithm. And it looks like this, and it's really, really not that pretty. Basically, what happens here is that we take the type from the type list that we've provided, and we apply this meta function that we also provided, and then we provide this already changed type to a new type list that we're creating. And we do that recursively during compile time recursion until the list that we provided in the beginning is actually empty and doesn't contain any more types. and then the recursion terminates because we hit our base case and we return the list that we've already created. But that implementation is not that optimal. It's actually it introduces a lot of overhead at compile time, and what we could do is that we could use again variadic templates and parameter packs, which make life a lot easier. So then we basically apply the meta function on each type of the type list by capturing the list into our variadic template, into our parameter pack. And what we effectively then have is we have a transform algorithm for compile time computations. So we have a type list, and we can apply a meta function to each type in that list. For example, remove const that we've already created, and then what we end up with, for example, in this case, with a list that that has all the types that have the const qualifier removed from them. And that's basically what I wanted to introduce in here. So what is actually template metaprogramming? That is, it can be actually understandable. It can be very useful. We've looked at type traits as a way of manipulating information, making some intelligent decision about types. The member detection trick, that's really clever, and the particular way of choosing implementation of algorithms at compile time, so you can choose the most efficient implementation as early as possible and in an efficient way. And also we've looked at the way of creating a type list container for type operations on some kind of containers at compile time. And that's all from me, that I wanted to show you here. So thanks a lot for listening.
Thank you, Miłosz. This is, of course, the time for questions. So if you want to ask a question, please raise your hand, and either me or Bartek are going to approach you with the microphone. Okay, we've got one question here.
Very simple one. Why Mikołaj Klatka, Nicolas Cage?
Basically, I had trouble finding the actual author for some of those quotes, so I just put Nicolas Cage in there. Any other questions about metaprogramming or about life in general?
We've got another one here.
What's the use of types list? I'm just curious. For what could I use it?
Well, it would actually depend on the particular design that you have. For example, what I use it for would be to implement a kind of state machine in C++, which could prove very useful. If that answers the question, well, that's a particular example that I came up with.
Okay.
Any other questions on this side of the room or the other side of the room?
Here we have a question.
Okay, in the front.
You mentioned that you work in the project which is using the template, and out of the tricks you showed today, how many of them is used in a real project?
I think each and every one. There is like literally not a single one that was omitted in this particular project, which is basically template metaprogramming, all that you could use and put in a efficient way, perfect way. It works perfectly, I promise. Try some of that at home.
What's the compilation time of your project?
It's comparable. It's okay. We're working on it. Next question.
Yeah, I actually know. Any other questions?
Okay, we
Back
have
in
here
the
a question.
front. Okay.
When you after set types list, I was expecting something like boost MPL vectors, etc.
Yes, that's a possibility. To use Boost MPL, and Boost HANA would be also another particular thing that we could use in here. But I wanted basically to introduce the whole concept of metaprogramming really in its guts, really in the way that is actually working, and try to do that in a understandable way, perhaps that is not actually black magic and it's something not that complicated, I
But-
guess.
But you use those in your project, right?
Yes, yes.
Okay, thank you.
We've got another one over here.
Okay, so let me ask about the limitation of the metaprogramming, because there are some issues with the when you want to deal with the floating point or not integers, and that's the one question. Do you have any solution how to overcome this limitation and perform computation on, for example, floating point numbers at compile time? And the second question is how to overcome the GCC, for example, or Clang limitation about how long the compilation can take. Because if we, performing some computation, the compiler may in some point say that it's end of the time that it's given. So how can you overtime this? Do you have any solution?
Well, to try to answer all that, about the floating point types, there's not a particular solution that I would provide. It's actually a limitation that you cannot have a floating point value as a template parameter, but maybe that would be some kind of solution that I'm not aware of. About the second thing, we were curious about the limitations from the compiler to the compiler. So, can you reduce your compilation time in some kind of a trick or some kind of?
I had an issue with metaprogramming algorithm for compiling big factorial numbers, and after 50 numbers, my compiler said that the timeout for the compilation is met and the compilation has to be terminated. So I don't know.
Really?
Have you noticed that kind of issue in your career?
Well, one of the ways, basically what I understand is to implement some kind of algorithm in a way that would be more efficient at compile time. So one of the examples that showed something a little bit like that is to use, instead of the compiler recursion tricks, use some kind of more smart implementation, like with the parameter pack one in the case of the type list. So that's one particular case. What is also I would recommend for actual debugging compile time code is there are some tools that we've used. I think they were called Template or Templar. It's actually a very neat, very nice graphical way to look into what's happening at compile time with template instantiations. So maybe that could help you.
One more question here.
I'd like to note that there is a kind of a hacky workaround to passing floating points as template parameters. If you Google Michael Park, he did a very good blog post on this. Basically, the trick is you make a macro that puts that value as a context for static member of a type, and then you can pass that type around and access the context for static member floating point at compile time.
Okay, that's really cool.
And as far as factorial, if you can use const expr functions, do factorial in those, but also
that's true.
Factorial 50 types. The other way to optimize that would be what's called fast tracking, where you would take, rather than one parameter out per recursion, you would make an overload that's specialized on, I don't know, there are 10 parameters left or 100 parameters left. Take all of those out and then do the factorial flat for the bigger chunks, and then so it'll take 10 and then 10, and okay, there are not 10 left, there's maybe 5 left, and then it'll take, 1 and then 1 and then 1 and then 1, and then it's done, right? And like stuff that size shouldn't be a compile time problem. If you look at MetaBench, also metaben.ch, it's Louis Dion, the author of HANA's compile time benchmarking library. Even if you're stuck with like Visual Studio's 2013 or something, there are already libraries that are order of magnitude or 2 faster than Boost that are on there.
And we use MetaBench too, by the way. We use everything. Yeah, it's really amazing.
Miłosz, do you have any final remarks, or do you want to accept the applause?
Well, the final remark will be, I think you're all aware that this was all actually a trap to get you to listen something about template metaprogramming, because nobody in the right mind will actually come to this talk if this was actually on the agenda. I'm kidding, of course. Let's take the applause.
Miłosz Warzecha, thank you.
Thank you very much.